Good afternoon. I'm David Hahn, the Craig M. Burge Dean of the College of Engineering, and it's my pleasure to welcome everyone to the final installment of the first round of our lecture series. We do plan to be back. Our goals remain to share our research success and impact with our alumni and friends, many who generously support the college and have truly helped to make this happen. Today's talk is entitled UA Goes Quantum, QUBIT by QUBIT. Now, every one of you have to stay tuned to learn what a QUBIT is. So many of us have lived through the birth of the internet age, and while we now move around unimaginable amounts of data, noting that US server farms consume about 2% of electricity generated in the United States, it wasn't always this way. You know, we used to move data around on tape and disk drives from location to location. Now we're starting down the path of a new computing paradigm, quantum computing, where information exists and is processed as quantum mechanical states. And you know, many of you thought back in physics, right? You didn't need quantum mechanics. It wasn't relevant to engineering. Well, look where we are now, which brings us to the need to move that quantum information around in a quantum network and ultimately a quantum internet. So I'm excited to learn a little more with you today about that. I'd like to introduce our panelists. So I have Dr. Bane Vasić. Bane earned his BS, MS, and PhD degrees in electrical engineering from the University of Niš, which is located in Niš, Serbia. He is currently a professor in electrical engineering where he directs the error correction laboratory. He was the architect of a leading detector decoder for Bell Labs data storage chips, which are considered the best in industry. And he co-founded a company called Coda Lucidia, a company focusing on error correction in flash drives. He is a Fulbright Fellow and a College of Engineering Da Vinci Fellow. My second panelist joining us today is Dr. Zheshen Zhang. He earned his BS in electrical engineering from Shanghai Jiaotong University and his PhD degree in electrical and computer engineering from Georgia Tech. Little history: Jiaotong University means communication and is one of the oldest universities in China, founded by the Ministry of Posts and Communications in 1896. So who would have imagined back then that one of their graduates is today building the quantum internet? He spent 5 years at MIT before joining the University of Arizona, where he is currently a professor in material science and engineering. He received the University of Arizona Award for Excellence at the Student Interface in 2018. So we're really pleased to have Zheshen and Bane join us today. Before we dive right into the technical details with their opening presentation, let me ask you one question first. Looking at our educational mission, how might educational institutions such as ours keep pace and prepare students to work in quantum beyond their university days, including supporting government agencies or commercial ventures? I'll start with Bane and then Zheshen.
So, you know, I participate in Quantum Economic Development Consortium. This is the institution that was formed by NIST. And we interview companies about their needs for quantum engineering programs. And they express interest in all types of degrees. So it is not only new graduate, it is also people who are already employed that wants to continue or change direction of their research or what they do. So at the university we are considering and we are working on these degrees and also programs that will enable this education. And we will address this in conversation with our guests.
Zheshen, what are your thoughts on that? You're muted, Zheshen.
Yes, I think workforce training and preparation is indeed critical for establishing an ecosystem for quantum technology. So in this regard, there will be a number of avenues we can pursue. So for example, sending students to do internships would build a bridge between quantum research in the lab and real world interests and applications. And this would also mutually benefit universities, national labs, and commercial entities. So I actually have seen a large demand from our industrial partners for recruiting internships to help expand their efforts in the quantum technology domain. And a second endeavor pertains to outreach activities such as organizing seminars to cover the appealing applications as well as fundamentals of the quantum technology. And as we see today, online webinars have now become a very popular and powerful platform to connect diverse communities and to disseminate the latest research outcomes. Nonetheless, we should not overlook in-person activities, because these would also be helpful to further spur interests and facilitate networking. So in this regard, we have arranged lab tours to show physically how quantum technology works. And specifically in a recent event, we organized a lab tour with IEEE Tucson branch and hosted more than 20 visitors from local companies. It was quite amazing to see the strong interest shown by our participants in emerging quantum technologies, and the discussion during the event were also quite inspiring.
That's great, Zheshen. It's nice to see that we're leading not only on the research front, but on the workforce front and on the outreach front. So thanks for that update. So as we've been doing, I'm going to now turn this over to Zheshen and Bane for a few moments to make a slideshow presentation and kind of set the stage for our Q&A. So I'll turn it over to you.
So you see my screen, is it good?
It's perfect, Bane. You're set to go.
So, Zheshen, you can.
Okay. Yes. Thank you for being here, and also we would like to thank Dean Han for inviting us to give an overview of quantum technology and with a focus of what U of A is currently pursuing. And here you actually see an amazing evolutionary trajectory of classical computers and networks. I think the video is off. So Bane, can you turn on the share
Yes,
screen?
I'm sorry for this technical. Is it better now? Something happened. I'm really sorry. So, and I lost the sound temporarily.
All is good right now.
Yeah,
it is good. It is good.
Yeah. Yeah, so it shows a amazing trajectory of the evolution of computers and the networks. And as you see, we 60 years ago, we have this very bulky computer system all the way evolved into a very compact desktop iMac that I'm currently using. And the same is true for the network. So in the 80s, we only have a network connecting a handful of nodes across the country. So now all our mobile devices and computers are all connected in the internet. So going forward, what is the next? So many people have envisioned a quantum computer and a entangled quantum network to connect diverse quantum devices. But now we may ask, so what is the fundamental difference from quantum computers and the quantum network from to a conventional computer and a conventional network? So this is something fundamentally different than just packing more transistors into a CPU to go from a 7 nanometer process to a 5 nanometer process to speed up. So there's some fundamental physical principles that enable us to build the next generation quantum devices.
So I would like to illustrate that this what is called quantum supremacy on a very simple example. So if you are connected to VPN, you are probably using RSA crypto system, and its security is based on difficulty of factoring large integers. So imagine that you are a hacker and that you want to factor some long integer of 2000, let's say 48 bits. So if you want to use a classical algorithm, the best classical algorithm for that, you will need about 10 years to run it. And you would have a server farm that is covering about 1/4 of North America. And it will be consuming a lot of energy. It will actually use entire world supply of fossil fuels in one day. And it will cost, of course, a lot of money. So quantum algorithms on superconducting quantum computer would do it in about 14 hours and occupy about 1 centimeter of space. And it will use less energy, but it is still expensive. So this engineering effort that we will be talking about today is really about that, about engineering quantum internet, quantum computers. So physical properties, physical laws are developed. So it is a very difficult but engineering challenge to build it. So now there are these two big resources that we use for quantum computers and communication. So in classical world, a bit can be, head or tail or 0 and 1. And in quantum, it can be, at the same time, both 0 and 1. And the proportion of how much is 0 or 1 is continuous. So imagine that now you have multiple qubits. Then the amount of information, you think of this as a memory, it will store exponentially larger number of information than classical. The second resource that we will be using is quantum entanglement. This is the fact that the states of two quantum particles are correlated. So in essence, these two particles don't exist separated, they exist together. And we will explain later how we use these resources. So now if you really want to do, instead of computing very simple functions, let's say inverting bits and using, let's say, 4 computers for different arguments, what you would do in quantum computer, you will combine all these inputs in one and then run it on the algorithm and you get answer immediately.
In addition to quantum computers and the broad quantum technology would also have profound impacts on multiple domains, including sensing, secure communication, and also simulations. So for sensing, people have already used the quantum state of light in gravitational wave detectors to enhance the performance of seeing gravitational waves. There's also a lot of applications in biological imaging and sensing. The fundamental principles of quantum mechanics also allow us to build communication systems with unconditional security. So which means the message you transmit can never be cracked by the laws of physics. And when applying entangled photons or entanglement in communication, you can also potentially achieve a higher communication rate. Another aspect of quantum technology is in doing quantum simulations. So we can take advantage of the fundamental quantum physics and use that to simulate another quantum system, which would greatly facilitate, for example, drug discovery and material design. Because in this case, you don't have to resort to a classical computer to do all the computations. You can naturally simulate the dynamics of a quantum system on a quantum simulator. And the quantum technology would also have impacts on fundamental science. So for example, now a emerging research topic is to build a connection between quantum information and cosmology. By understanding the fundamental properties of entanglement, we may be able to build a link to understand the dynamics, for example, of black hole, so that would actually deepen our fundamental understanding of the universe.
it is very interesting what Zheshen says, because quantum physicists, theoretical quantum physicists, are now obsessed with error correction, and there are even theories that connect space-time with error correction and black holes. So it is getting connected.
Yes, and due to these appealing features of quantum computers and quantum networks, so now there's a quest to build a global scale quantum networks that interconnect distributed quantum computers. So in this regard, many countries have launched their the so-called quantum initiatives. So for example, China has sent satellite, which we call quantum experimental satellite, and to form a space and ground quantum communication network. And the UK is pursuing a similar effort, which they call a quantum communication hub comprised of multiple nodes connected by quantum links. And in the US, we have published the strategic plan for building quantum networks. And since last year, we have also significantly invested on quantum computers and quantum networks. As you see, there are some new centers recently formed. So actually, what we will introduce later is a engineering research center led by U of A to develop quantum networks. But we also have other centers at other universities and national labs to work on different aspects of quantum computing and the quantum networks. So the investment has been 750 million last year, and the projected investment in the next fiscal year is around 700 million as well.
So you maybe saw this in the news recently about the Center for Build a Quantum Internet. So I just got, I had finished the meeting an hour ago with Fermilab about organization of this project. So this is, it feels like building a spaceship. So it is really enormous effort. It has a lot of participants and partners. And it is addressing a fundamental problem of coherence time of qubits. So you want these qubits to stay stable longer to be able to do meaningful computation. So this center addresses all key aspects of computing and sensing. And what is very interesting for us is that it has ambition to become a national hub for hosting large and unique experimental test beds. So many of the things that we develop in our labs or theories that we develop, algorithms, could be it would be possible to implement using facilities in Fermilab. So this is our team, and includes also Zheshen Zhang from our college. So now maybe we talk a little bit about technical things and this quantum error correction that I told you that how physicists are excited about. So, and you know, ensuring coherence time and stability of qubit is recognized to be very important. So how do we actually do that? How do we correct errors? So, so imagine that we have some particles and they, you know, they can be in some state. So what we do is we entangle them. And similarly, as we can entangle, you know, two particles, we can also entangle more of them. So now the information is encoded really in this entanglement of particles, of qubits. So what you do is, actually we call this stabilizer. So we will have operation that stabilizes these qubits. So now we can have multiple qubits, and groups of qubits can be stabilized in some network. And this graph where this black node denotes stabilizer and red nodes denotes qubits is something that, you know, that make these qubits exist at the same time. So they are not separated anymore. They don't live individual lives. they're all part of this information, of this encoded information. Now, computation must be done on these objects. So now, of course, you can say, well, this error correction, it is a pretty old theory. It is developed theory. We use it in Flash. We use it in communication. So why I just don't take some of the tricks that we use so far and implement some of the codes, good codes that we already have. So of course, it would be nice to do this, but it is not quite possible. And there are some really cool, some really nice problems that we work on. For example, you cannot just copy like triple modular redundancy that we use in classical systems. You cannot just copy unknown qubit. It is not possible for quantum state. Then you cannot just read the qubit from a memory or observe it because you will destroy it. And plus, quantum gates are very noisy. So the question is, how do we first can correct qubits or the state or code word without even looking into it? And secondly, how errors can be corrected when the hardware that corrects these errors is also noisy. So, but the theoretical answer to these are that this is actually possible, and these are kind of algorithms that we use. These algorithms accidentally were discovered also in artificial intelligence, but they're discovered also in coding theory before, where you allow only local computations and local propagation of messages that will make it will make this processing fault tolerant. Secondly, it has to be very fast, and it has to consume less energy. You don't want to dissipate heat that now your refrigerator needs to cool at 0 Kelvin. So in other words, these are kind of things that we are trying to address in both of these centers related to error correction codes.
So once we build a quantum computer with the error correction code, and the next thing we may think about is to find a way to interconnect them. It's just like our internet now connects all the mobile devices and the computers. So in this regard, U of A also has a strong effort in building quantum networks. And this effort actually was initiated about 3 years ago. 2 years ago, we were awarded a NSF major research instrumentation program to build our current on-campus quantum network testbed. So this all the fibers have already been deployed. So now we have a on-campus quantum network connecting 5 different buildings with more than 100 fibers and more than 10 laboratories are involved. And by using this quantum testbed, we can send entanglement, entangled photons from the central hub, which sits in the ECE building, to different labs on campus. Now they can use entangled photons in their own experiment to advance their own discipline, and they can also send photons back to the ECE central hub to access the single photon detector capabilities. And this is called the Interdisciplinary Quantum Information Research and Engineering Project, or INQUIRE for short. Last year, we further built upon INQUIRE and also partnered with a few partner institutes, including MIT, Harvard, and Yale University, and others. We were awarded a center, NSF Center for Quantum Networks. So the objective of this center is to lay the foundations of the quantum internet. And the role of U of A is to provide this testbed capability and to assemble different quantum devices and quantum systems to offer critical functionalities for our future quantum net. And these key elements include, for example, quantum repeaters that would allow for long distance distribution of entanglement, and also the integration of different devices into compact quantum systems. From the audience, there's a question about what you can do with a quantum network. So here is an example of the application of a quantum network. So actually in my lab, we have already demonstrated a tabletop setup of entangling different sensors. So as you see, we can now use entanglement to link different sensors, and we show that when they work collectively by their shared entanglement, now they can achieve a much better performance in detecting radio frequency signals. And this would be a critical functionality, for example, for navigation and positioning applications. And on the right, this is a figure of our experimental setup, and this figure is also shown in my Zoom virtual background.
So in this, sorry, Zheshen, I wanted to mention that also in this project with Fermilab, they are interested in detection of gravitational waves, and this setting can be prove useful for this application as well.
Yeah, that's right. So this would also serve as a fundamental tool to explore fundamental physics. So for example, detection of gravitational waves, or the detection of dark matters and dark energies, where you really require very high sensitivity. So that's an example of sensing, quantum sensing. And there's also other examples of entanglement-assisted communication. And this is also a collaboration work with Professor Untitled Chapter in ECE. So in this work, what we demonstrated is that if, let's say, two users, Alice and Bob, and they pre-share entangled state, now they can take advantage of their pre-shared entangled state to establish a reliable communication link even over a very lossy and noisy channel, and they can actually do much better than without using the entangled resources. And as you see on the right is a proof of concept experiment in which we have implemented a entangled photon source along with a novel quantum receiver to reap the full benefit of pre-shared entanglement. So going forward, so a lot of the experiments have been proof of concept, but to widely deploy the quantum technology, what we really need is an integrated solution, a compact solution. So this is another research direction that my group is pursuing. So we are developing integrated quantum chips to host all these quantum devices. So as you see, a fabricated quantum chip would be, compared to a $0.25 is much smaller than the size of a $0.25. And now we can integrate a variety of quantum components onto the chip, and now we can generate entanglement on chip, and you can also build quantum sensors on chip. So this is going to provide a much more scalable, robust, and mass-producible solution for our future quantum technology. So here is a list of some of our ongoing projects, so including the two centers that Bane already mentioned, and along with other research projects. And as you see, U of A has a strong focus on quantum networks and quantum error correction, but we also have ongoing grants on quantum sensing, and we have established close collaborations with the industry as well to foster the technology transition.
So that's about what we want to present. So we are welcoming your questions and comments.
Excellent. Thanks, Bonnie. If you want to unshare your screen, we'll
I will
move into our Q&A. Thank you. That was a really informative presentation, and these are tricky concepts that even engineers and experienced engineers still struggle with, and we've had some questions that we're going to go through now that were pre-submitted, and I've also trying to pull in real time from the Q&A. We won't get to everything, but we'll do the best we can. So let's build on this presentation and kind of go back to that complex problems made easy. So, how would you explain the quantum concept, quantum technology to an engineer that doesn't quite get the concepts of things like entanglement and qubits? I guess what I'd call your elevator speech. Your kind of 1 minute Quantum 101 highlights. So Bane first and then Zheshen.
So probably in the elevator, it would be hard to explain quantum mechanics, but I can tell you that at parties, we have a lot of fun. People are fascinated by these things. And of course, as engineers, we want to build things. So fortunately now, I think the good example is that compare this state where we are now with the development of electrical engineering. Remember, when Maxwell and Faraday had their equations, and it was still physics. So, and then eventually electrical engineering appeared as a discipline. So it is the same thing now. So in order, you don't have to go into laws, into quantum mechanics to explain hardware design. So you don't need to know all this. So it is similar as a computer. What I would do is explain to engineers that it is, that we have quantum circuits, that we have quantum gates. They are actually vector matrices. So there is more variety of quantum gates than in classical, but we still live in a complex Hilbert space, and we have strange operators that act on this, but it is not very complicated to get. So I like probability. So I also like to think of this evolution of a quantum system as a finite state machine. Now, except that now these matrices that you are using to express probability are can be negative and can be complex. So these are all generalization of permutation matrices. So of course, there are a lot of really good books now that are written for quantum information science and engineering. And there are of course these resources that look strange. And of course, not physicists make things difficult with strange notation, but these are just vector spaces and Hilbert spaces, nothing, and a little bit of probability. So it is not, if you really, if it's too simple for you, then maybe you can go to particle physics and go to quantum gravity. But for our engineering purposes, we are good.
All right, they're just parts in a circuit. Zheshen, do you want to take your shot at quantum made simple?
I think I will probably first start with describing the intriguing applications that quantum technology enables. This is because everyone desires faster computers, more secure communications, and higher resolution cameras, for example. This is an example of improved sensing capabilities. And then I believe, discussing the prospect of quantum technology would further spur strong interest, and which will in turn lead to questions like, wow, how could this even be possible? So now it becomes a good opportunity to explain to the audience some fundamental principles of quantum technology, such as superposition and entanglement, using simple examples such as the spinning coin example we used in the slides. These examples are not perfectly precise, but nonetheless would be illustrative. So I think, in this regard, those are good examples to illustrate to the broad audience what are the fundamental principles of quantum technology.
Okay, thank you for that. So before we dive right back into technical aspects, some have asked about the educational aspects once again. So what about the possibilities of developing an entire PhD program specifically in quantum? Is that feasible, and what would be the key disciplines, Bane?
So, I mentioned this Quantum Economic Development Consortium and the Workforce Development Group. So these are excellent questions, and this is exactly what this committee is about, to define this program. What are essentials for this program? What is really essential courses that students should take? So we interviewed companies, and interestingly, what is essential depends on companies, depends on the size of the company. So for example, whereas larger companies would emphasize maybe quantum algorithms, smaller companies would emphasize physics and large scale accessibility to large scale simulators. But what I found really amazing is that everybody emphasizes that people need more engineering skills. So they have even kind of funny expression for this. They say screen-based skills. So screen-based skills is not sufficient for this. So for what is we are looking. So you know, we also have to remember that we are offering, we don't have a program, formal program in quantum engineering, but we are offering courses. So many professors and students are taking these courses that are offered at the University of Arizona. So the answer is also about this program is complicated because there is a variety of ways that this can be done. And in this consortium, we hear different opinions, different perspectives. For example, Canadians have formal programs. Yale, for example, doesn't even have an official program in quantum engineering, although they have very good research in quantum. So, so at the university, we have resources, and this center that we got will also facilitate developing the program. And it is also a question, you know, how to do it. So we cannot start with, it seems that it is not wise to start with quantum mechanics and a lot of theory. So, so typically you learn about vector spaces and kind of simple quantum algorithms before you go into the lab, and then if you do more in-depth education.
Okay, thank you, Bane. Zheshen, let's kind of dive back into the science and talk about how data is actually stored. So what about the idea of entangled particles as being single atoms or single electrons? Can that play a role in quantum science? And I'm also going to grab a quick audience question and throw it on top of this. That's cosmic radiation. So do cosmic rays, you know, mess up your test bed if a ray passes through one of your repeaters? So that's an easy one, and then I'll let you answer the larger question.
Yeah, that's a great question. So I also saw a number of questions about entanglement in the Q&A box. So first, you know, if we want to understand entanglement, I would say entanglement is just a very, very strong correlation between two or multiple objects. And the correlation is so strong that you cannot actually cheat these objects individually. So you have to consider them as a global system, as a, you know, a single system, okay? And entanglement plays a critical role in quantum science and technology. And we have already seen in the presentation, we can now entangle multiple sensors to demonstrate measurement performance superior to that achievable by individual sensors, which means they are not entangled. Okay, so we can also leverage entanglement to enable faster and more secure communications. So by far, our research has been focused on traveling qubits. So which means entanglement is carried by photons, you know, moving around. Okay, but one of the major research activities of our new Center for Quantum Networks is how we're going to interface these traveling qubits with stationary qubits carried by, for example, artificial atoms. Okay, so that now you can not only send those entangled photons around, but you can also store them and locally process quantum information, just like what we do with classical memories and CPUs. So in this regard, so there's another question about cosmic radiation. So, you know, that's a very good question. So there's a recent work from, I think from MIT showing that this radiation may prevent you from building a quantum computer. But I want to emphasize here that our technology is a bit different than, you know, all other superconducting based technologies. So which might be more prone to radiation, cosmic radiations, because, you know, these are subject to a reduced decoherence time. So our technology is more based on photons, so which are not inherently subject to these radiations, and we can actually maintain quite long coherence time carried by our photons. And also, you know, when we talk about these stationary qubits, those artificial atoms, we can also convert the quantum state carried on the photons to a quantum state carried by those artificial atoms, and because those are not superconducting devices, so they are less vulnerable to this radiation effect.
Thank you. Bane, you have a lot of experience in data storage. So how will quantum networks, quantum computing possibly lead to unhackable data storage or an unhackable internet? And ultimately, does this give us more practical products that help us in that aspect?
So unlike previous schemes that would ensure, that attempt to ensure security that is based on algorithm or difficulty to solve some problems, there are some physical laws that are behind security of quantum systems. So the Heisenberg uncertainty principle dictates that, you know, if an adversary tries to observe what is transmitted, then if the hacker attempts to observe the quantum information, it collapses. So there are numerous theoretical results about provable secure communication and networks. So there is even research about how to make communication that is not observable, that you cannot prove that we communicate. So the future of this quantum internet is also envisioned as having a service provider. We pay it, and the service provider gives us a service of providing us this entanglement. So if Zheshen and I want to communicate, we need the entangled photon. We pay some money, and then we get these photons, and then we communicate. So of course, I'm sure that in the future there will be attempts to kind of attack these systems, and as we know that it always comes from some human factor, or some other trick or some vulnerability. So maybe this would be hardware attacking, or hardware or physical presence at nodes, or damaging them. But based on these fundamental physical laws, we know what is secure, what is not. And we know these bounds for quantum systems.
Thank you. So Zheshen, a lot of people see the quantum internet as the new world space race to the moon, back in the 60s. What is the international landscape like? Is it collaborative? Is it competitive? And how do you see the United States with regard to our competitive advantage right now from where you sit?
Yeah, that's a very good question. So by far, I haven't seen a direct competition because different countries have very different focuses on the development of the quantum internet. So my understanding is that the objective of the US is to develop enabling technologies for long-distance entanglement distribution, which represents actually a one step forward beyond many other countries' current endeavors of point-to-point quantum secure communication, which does not need entanglement. But I do see the investment on quantum technology from the US government, private sector, and even our college is wise and visionary. But I also see, there, however, remain many unsolved fundamental scientific problems, such as understanding the structures and properties of complex entangled states. So in this regard, I believe international collaborations would be an effective approach to tackle these fundamental challenges.
That's good. I think that this, this discussion has been really enlightening about what we're doing at this university and how you both are sort of on the very, very forefront of a very complex field. I think you've also demonstrated that these things are complicated, and it's sometimes hard to put them into simple words. So in the few minutes that we have left, I'm going to ask each of you to kind of pull out your crystal ball and let's look 20 years ahead and just briefly tell us, what do you think will be solved and what do you think we'll see? And I'll leave it to you, Bane, and then Zheshen for the last word.
So again, I can tell you what I know from theoretical computer science. And but I thought a lot about this question in the past. So theoretically, it is unlikely that quantum computers will be able to solve the worst case instances of NP-hard problems. But they will likely to find approximate solutions, good approximate solutions, and do it faster. Playing chess, scheduling airplane flights, and for example, very attractive feature of automatically proving theorems are hard even for quantum computers, and for artificial intelligence. So this generalization of things are kind of that we humans still kind of better than others. But I think there are also, quantum is not everything. There are other important questions. There are questions that with increase of these capabilities of computing, that we have also computers that are capable to do many things. So now this brings the question of our relationship between our individuality and society, and us humans and machines. So the modeling psychology or consciousness and cognition is something that quantum computers will be probably good at. So you see that this can have a profound effect on society, and I don't think that we are even able to predict this impact. And it is very interesting that in this center that we mentioned for quantum internet, the big part of the center is also studying this impact of these technologies. And of course, we cannot make predictions, but we cannot just ignore it. So it is good to think about, because there will be good and bad things as well in technology.
Thank you. Zheshen, pull out your crystal ball and tell us what you see in the future.
I think 20 years from now, quantum technology would already be deployed to enhance the performance, for example, of sensors, and also to efficiently solve some special optimization and data processing problems. And then the next critical challenge would be laying a foundation for a scalable architecture for quantum computing and the quantum sensing. So when you have a number of qubits or quantum sensors, how do you scale up to billions of them? Okay, so this is also a challenge for the classical computer and sensors, and they have already addressed this. So if we look back on the evolution of classical computers, it actually followed a very nice trajectory known as Moore's law. Okay, and I believe we will need a counterpart for the quantum technology.
Gotcha. Well, maybe we'll have Zheshen's law one day. I want to thank you both for sharing your insight. You're really doing great things. Again, you've put the University of Arizona clearly at the forefront and on the nation's map of quantum, and we're really grateful for that, along with your colleagues, many colleagues on this campus, and we appreciate that. I also want to thank our audience for joining us once again for learning the things that are happening in this college. I hope you walked away with a little bit better understanding of quantum, and I hope you continue to learn about that. So I want to thank everybody and wish everyone a good day. Bye.
Thank you.
All right, thank you.